My name is Mariusz Postal. I would like to invite you to participate in the video publication titled Information Computation Fundamentals. It is a contribution to the Programming in Practice series of publications. The main goal is to recall fundamentals concerning information computation. At the end of this video, you will distinguish the differences between information versus data, and algorithm versus program. You will be aware of the necessity of using these terms in proper context, though they sound similar. As usual, let's start defining the main objectives, by defining the topics we may encounter in the context of the background knowledge related to programming in practice. As a contribution to the explanation of fundamental terms, let's continue the discussion on data and computer programs in the context of information processing. So, the terms information versus data and algorithm versus program require clarification. A computer may be recognized as a technology used to process information. In other words, we are talking about applying technology to information processing. In this context, information should be recognized as a piece of knowledge about the state or behavior of a set of activities. The activities that we want to monitor or control, with the use of technology, or more precisely, with the use of physical programmable devices, to achieve problem solving automatically. In other words, to leverage automatic information processing. It is our goal and responsibility, as computer science active members of an ecosystem, shortly developers. I must say that I have a few problems with this approach or explanation. The first problem I have is the term information processing itself. Let me ask you a question: do you think that medicine, or journalism, is not concerned with information processing? It is a vital question for further discussion, because we need to distinguish between what doctors and journalists do, and what you will do as a software developer. Additionally, let me stress that doctors and journalists also use technology daily. This question is the easiest one to answer, because we can say that computer science deals with the automation of information processing by applying programmable devices, I mean computers. Thanks to this, we can say that computer science is also an engineering domain, aimed at providing solutions, information processing systems deployed atop computers, and programs to be used in medicine, for diagnostics, or journalism for newspaper publication. We may recognize the information as a piece of knowledge about the state and behavior of a selected real-time set of activities, part of the natural realm. But to solve any problem using a computer, we also need to know how to process the information to reach a goal. Again, we need information, a piece of knowledge, describing how to solve the selected problem. How to control the activities to achieve the goal we are facing. This kind of knowledge we call an algorithm. Let me stress, it is also information that cannot be directly applied or used by any physical device, including but not limited to computers. In conclusion, the main goal is to address a fundamental inconsistency. How to process something abstract, namely information using a physical device? The automation of information computation requires the use of technology, simplifying a computer. Any computer is a device. Hence, it is governed by the laws of physics. Here, we come to our fundamental inconsistency: how it is possible to use a physical device, the computer, to operate against abstraction, information. To solve the problem, to resolve this inconsistency, let's try to address this issue by answering another question. Is the left side equal to the right side? The first answer may be based on the observation that what we see on the screen are characters. That is, on the left side of the equal sign, we have two characters, and on the right side, we have one character. From this fact, we can conclude that the left side is not equal to the right side. Generally speaking, we use characters in the syntax analysis. In this discussion, the set of allowed characters that we can use, concatenate, to make a valid stream, is called an alphabet. If the alphabet is intended for a human, it contains alphanumeric characters, for example, letters, digits, or symbols, for the Latin alphabet. In the case of today's computers, which are governed by the laws of physics, we must consider only two discrete states. It makes a difference because in this case, the alphabet must contain exactly two signs. Following this rule, the alphabet is called a binary alphabet, no matter what signs it contains. In case the alphabet is intended for a human, we are talking about characters. In case the alphabet is intended to be used by a computer, we are talking about signs. In both cases, we are talking about the alphabet as a set of entities to be concatenated in streams. For the characters, we have a shape. In the case of signs, we have measurable features. If we move from a syntax analysis to a semantic analysis of what we see, we can claim that the left side may represent the number 4. And the right side can also represent the number 4. In that case, the numbers are equal to each other, so the equal sign is legitimate, because both sides are equivalent. That could have the same meaning. Only one question remains: what conditions must be met for the left side to represent the number 4, and for the right side to represent also the number 4? In this case, we are comparing the meaning, but not the streams of characters. Again, meaning is an abstraction, so physical computers cannot be able to compare meanings. They always compare bit streams, and they always work on bit streams. Continuing this discussion, to resolve any doubts related to the meaning of the information and data terms, I use a funny illustration, in which the number 4 is presented as a ghost. Something that doesn't exist in the real world. It is information. It is an abstraction, but it has two equivalent representations interconnected by arrows indicating a bidirectional relationship with the streams of characters associating a meaning to them. To stress the difference between information and information representation associated with streams of characters, the representation we call data. To build a meaningful relationship between something abstract, in our case a number, and something that has a physical nature, a sequence of characters, we first need to define the alphabet, a set of allowed characters that you use in this sequence. Then we need to define a set of rules expressing how to concatenate these characters into valid sequences, called syntax. Finally, we must define the semantics, rules we could apply to correct character streams to associate meaning to them. Finally, the alphabet, syntax, and semantics make up a coding system. Again, we can observe that in reality, we are computing the data but not the information. Hence, someone could put forward a proposal that maybe it is enough to replace the term information with the term data, and as a result, we will be able to avoid this whole long introduction, which is relatively low level and theoretical. Of course, the answer is that we can't do that because your duty, as a software developer, is to select, or if necessary, even create an appropriate coding system. The good news is that the creation of a new coding system is built upon the existing ones. In other words, typically new coding systems are derived from the existing ones. In any case, it is part of your responsibility, so you must know how to deal with it and acquire appropriate skills. Automation of information processing involves a computer, a physical device, resolving a problem as a series of actions, or steps to achieve a particular result, or help fulfill a task. To talk in the context of problem solving using a computer, we need to know how to compute the data to meet the business process expectations. Again, we need knowledge, a piece of information on how to solve the selected problem by applying a computer. This kind of knowledge we call an algorithm. The first challenge we must encounter is that information is abstract. In other words, it is knowledge that cannot be used directly to describe computer behavior. We must be aware of how to describe the actions, or steps to achieve a particular result, because the computer is a physical device and cannot process any abstraction. Again, let me stress that the algorithm is information that cannot be directly applied or used by any physical device, including but not limited to computers. Computation means a set of actions that ensure the automation of information processing. To ensure automatic processing, we need to use technology, which means a programmable device. Today it is a binary computer for sure. Anyway, we must ensure that this processing engine behaves in compliance with an appropriate algorithm. The algorithm is again information because it is a piece of knowledge on how to solve the problem. Hence, it is an abstraction that will be useful in the computation process only if it can be represented in binary form, similar to the process information discussed earlier. Algorithm implementation is the next task of software developers. A result of this work is a computer program. That is a recipe instructing the computer how to control the activities to achieve the chosen goal. Information to be processed by a physical device must be represented as data first using the alphabet, syntax, and data semantics. That is a coding system. A similar approach can be applied to the algorithm, which is also a piece of information describing the computer behavior, shortly algorithm. The most promising solution is integrating custom coding system design and algorithm implementation because both are tightly coupled. Today, we do not need to implement the algorithm using a binary representation. Thanks to the compilation process, we can use alphanumeric alphabets, just like the natural languages we use daily. Typically the implementation alphabet is derived from the Latin alphabet. This leads to the statement that at the beginning of its life cycle, any program is just a text, a sequence of characters. Text becomes a computer program when it meets additional rules that will enable it to be compiled. And so we come to the term programming language. To be used to control a computer, the role of the programming language is a kind of contract between the software developers and compiler that both must comply with. It is a foundation for the implementation of information processing, as data computation. It must be a set of rules. The contract must be exhaustive. To fulfill this requirement, the syntax and semantics must be defined and applied respectively to provide appropriate rules that can be used. C# is the language that I use to explain software development issues, with concrete examples and compliance with programming and practice principles. Using an alphanumeric instead of a binary alphabet, and the requirement that the design of the process data coding system should be coupled together with the algorithm implementation, leads to a need to replace the coding system with the type concept to design the information representation and computer behavior. Defining a programming language atop of alphanumeric alphabet allows us to better suit this language to human needs. Finally, we get high-level languages. To describe the behavior of a binary computer, we need binary programming languages. The binary programming language is a set of semantics rules, syntax rules, and a binary alphabet. The binary alphabet is a set of allowed signs that contain exactly two entities. This kind of language is well suited for a binary machine but not perfect for humans. Hence, nowadays, we are using high-level programming languages that have an alphanumeric alphabet and syntax and semantics rules optimized for human use, for example Java, C#, Python, etc. The cost of this approach is that the program text must be converted, for example using a compiler, to binary language somehow, or interpreted to be executed. Information technology science addresses the automation of information processing by employing computers. Information should be recognized as a piece of knowledge about the state and behavior of a set of activities. Hence, the information is abstract and cannot be directly subject to computer processing. To resolve this inconsistency, we are using data as information representation. If something is a stream of signs, and we can assign a meaning to this stream, it is just data. Again, computers cannot be able to deal with meanings, they always process bit streams. Representation of information is resolved using a coding system. To integrate custom coding system design and algorithm implementation, the type concept is embedded in all recent high-level languages. Thank you for watching. To follow me, watch or star the repository with the extended examples on GitHub. If you have questions or doubts, contact me by Gmail. com@programmingandpractice24. Let me invite you to visit Mariusz Postal's profile on C# Corner.